All right, so what I want you guys working on is, okay, from your booklet here, actually that's not the one I want to have open. I want you guys to start at the end of the vertical circular motion question, so that would be like the end of page 3, okay, and work upwards. And then if there's any that give us trouble, we'll go through them, and then we're going to move on to orbital mechanics today. So we're going to be kind of done with the principles of circular motion and moving on to orbital mechanics, gravity, okay, and things like that. So that's the one we want. I think the hamster that was in my computer is getting tired. Slower. There we go. All right. So let's have you guys start down here at number 11 and work your way back up instead. Okay, so you get a couple of these tougher ones. Okay, I'll go through any that give us trouble. We'll work on that for maybe about the next 20, 25 minutes. Okay, and then I'm going to talk about Kepler and Cavendish and orbital mechanics. All right, so for number 9 here, we have a 5-kilogram object. So we know its weird. We know its mass, okay, is 5 kilograms. Okay, and we know that it's undergoing uniform circular motion. There's the key. Okay, uniform circular motion. Is this a vertical circular motion question? I tricked you. Okay. I once in a while I do that. I just throw a question that doesn't belong on a worksheet on there to see if you're reading them carefully. But we'll go through it anyway. Okay, so it's undergoing uniform circular motion and it takes 3 seconds to make one complete revolution. So the period is 3 seconds. The radius of the circle is 4.0 meters. What's the centripetal acceleration of the object? Well, centripetal acceleration equals v squared over r, right? I don't have v, but I have the formula for v, 2 pi r over t. I'm going to substitute that in to this formula here by squaring it. So I'm going to have 4 pi squared times r squared over t squared times r. All right. I've got an r on the bottom and an r squared on the top, so the squared goes away on the top, the r goes away on the bottom, and now I've got my formula. So I'm going to go 4 pi squared times 4, 4 meters, the radius, okay, and then divide that by 3 squared, and that should give me my 17, not 1.7, 17.5 meters per second squared. Okay, everybody all right with that one? Okay, and then for part B, what's the centripetal force? Well, there's actually a shortcut on this. You could do all of this again, okay, and go Fc equals mv squared over r and plug all of that in for v. Or you could recognize that you just calculated this, right? And that Fc equals mass times centripetal acceleration. And you already have the centripetal acceleration, and the question told you the mass was 5 kilograms, and all you have to do is go 5 times 17.5, and you'll get 87.8 newtons and save yourself a ton of work. Okay. Any other ones? Okay. So expect that those are the kinds of questions that are going to show up on quizzes and tests. Okay. Tomorrow you're going to be doing your assignment on circular motion, so you'll see some questions like that, some curve questions, bank curves, non-bank curves, stuff like that on there. All right, if there aren't any other questions, then we're going to move on to orbital mechanics, which has to do with some interesting feuds that went on in the scientific community. There was like a lot of hate back in the day, when they were trying to figure out what planets and stars and stuff really did. Probably the most involved one of these feuds was between Johannes Kepler and Tycho Brahe. Back in the time when Kepler and Brahe lived, most people and many scientists still believed that everything orbited the Earth. Okay? The terracentric universe is what they believed in, or the terracentric model. The reason people believed that was because they could observe the movement of things in the sky. They saw that the sun would go around like this, okay, or over the Earth or whatever, okay, that made it seem like the Earth was stationary and everything else was moving. All right, and that led to, pretty good understanding of how things work. They could see that stars moved, okay, throughout, moved in the sky through the night. Stuff like that. You guys ever seen like a time lapse of night? Like it looks like the stars actually move, because it's not the stars that's moving, obviously it's the Earth that's rotating under them, but people didn't know that, okay? And what they observed made more sense than things they couldn't prove. The problem is that not everything in the sky did that. Some things moved erratically, okay? That's why planets got their name. And what does the word planet mean? It actually means wanderer, okay? Because unlike other things in the sky, planets didn't just go across the sky. They would periodically do different things, okay? And not move like all the other stars did. So they were called planets, they were wanderers. At that time, nobody knew exactly why they did that. They just wandered, so they were wanderers, okay? So people made all these observations, especially Tycho Brahe. He spent his life charting the movement of the planets in the sky, okay? Not always with a telescope, okay? Like this is kind of pre-telescopic observations and things like that. He just watched planets move in the sky. And he found that most things just went over, okay, and did their thing. But especially for Mars, he noticed that instead of doing what all the other bodies did, which is just move in an arc past the Earth, okay, Mars would do this periodically. It would move in the sky in a very predictable way, and then it would backtrack in the sky, and then go back along the rest of the arc. Okay? This was hard for Brahe to explain using what he believed to be true, which was the terracentric model. If everything orbited the Earth, why did Mars stop, turn around, go backwards, stop, and then turn around and go forwards again in the sky? Okay? It didn't make a lot of sense. So he needed a mathematician, because he couldn't make the math of this movement in the sky, this orbital pattern. He couldn't make it work. And he just figured, well, math's not my thing. I'm not a mathematician. I can do math, but I can't make the math of this movement work. So I'm going to hire a mathematician to prove that Mars does actually orbit the Earth. So he hired Johannes Kepler. Now, Kepler didn't believe in the terracentric universe. They didn't get along, even though Brahe had hired him. Okay? But mostly he hired him to keep him busy. So he gave him his life's work. Tycho Brahe's life's work was charting the movement of all these things, especially Mars in the sky. And so he gave him these volumes of material, books upon books of his notes and diagrams and stuff, and said, make the math work. Go away now. Okay? And so Kepler goes away and he's looking at all this stuff and he's looking at these observations, and Tycho Brahe's observations are immaculate. Okay? The guy has spent his life making accurate observations of the movement of things in the sky. Tycho Brahe's working on Kepler's working on the math, and he can't make it fit with the terracentric model. But he can make it work if the sun is the center of the solar system. The math is really easy. I can make it work like that if the sun is the center. Tycho Brahe says, no, that's not what I said for you to do. Make the math work for what I said. Kepler said, I can't. You're wrong. And Brahe said, you're fired! Because that's not what I hired you for. I hired you to do the math and make it work. And Kepler said, I can't. You're wrong. And so he got fired and he went away and he took Tycho Brahe's life's work and used it to prove him wrong in the scientific community. Yeah, that would be a pretty big sword, like right through you, okay, like right through your heart. Okay, your whole life's work used to prove your strongest belief wrong by the guy you hired to prove it right. So you can understand there was little bitterness, okay, between Bray and Kepler, okay? And so that started the feud. And Bray went to his grave still believing in the terracentric model, okay? Even though now, of course, we know it's not true. The only reason that Mars would have a movement like this in the sky is because Mars and Earth orbit the sun. So the sun is here, okay? Earth is orbiting inside of Mars. So Mars appears to move backwards in the sky anytime Earth passes it. Okay? It's like if you pass a car on the highway, right? If you just look to the side and look at the cars you're passing, and it looks like that car is moving backwards. It's all about relative motion. Okay? Because the Earth is inside of Mars compared to the other planets, okay, it will pass it because it's moving faster. From our perspective, it makes it look like Mars is going backwards because it's falling behind us. Mars isn't moving backwards, it's still moving forwards, but we're passing it. Okay? But in the sky, it does make it look like it goes backwards and then turns around and goes forwards again. Okay? The only way that could be explained was if both of them were orbiting the sun and Earth was closer to the sun than Mars. Kepler could make that math work, no problem. Okay? Bray just didn't like it. Right? In fact, it was Bray's observations that proved that the terracentric model was wrong. Okay? So that kind of sucked for him. All right, so Kepler takes all of these observations and he comes up with the 3 laws, okay, that basically govern the movement of planets around stars and basically the movement of anything else that's gravitationally bound to something else. The thing that's brilliant about Kepler's work is not that he figured out everything moves the way it does, but that he did it before anybody had really quantified what gravity is and the role gravity plays in making things orbit other things. He proved all of these celestial mechanics with basically no knowledge of the force of gravity. This is strictly from observations from the ground on Earth. Okay? So that's the amazing part of it. He made all that math work and he didn't know about how Earth is gravitationally bound to the sun, okay? And that kind of stuff. All right, so Kepler said everything in our solar system orbits the sun, but those orbits are not perfect. They're not perfect circles. Everything orbits in an ellipse. Okay, he called it the Law of Elliptical Orbits. Okay, so basically what that means is there are points in the Earth's orbit where it's closer to the sun than others. This is obviously greatly exaggerated. Okay, we do not get that much closer to the sun, okay, in our orbit. If we did, we would consecutively freeze and fry, okay, every year. That's not what happens. All right. So there are points in the Earth's orbit where we're closer to the sun than others. Okay. So when are we closest to the sun? Summer. Nope. Spring. The seasons have nothing to do with this. What causes the seasons? The tilt of the Earth. Okay. We're actually closest to the sun right now. Okay. In winter, we're actually closer to the sun. Okay. I think perigee is, I'd say it's early December, or is it early January? It's basically in the dead of winter. Okay? And then we're actually at apogee furthest in the summertime. Okay? So Earth has a tilt. Okay? Our axis is tilted 23.5 degrees from vertical, which is actually quite a bit. Okay? As the Earth goes around the sun, okay, the poles are pointed either away from the sun. Right now we're pointed away. Right? So just a quick review of what causes the seasons here. No, that's not going to work. Okay, here's the sun. Okay, the Earth is in this orbital plane here. Okay, in winter, okay, Earth is tilted like this. Okay, the North Pole is tilted away from the sun, which means when the Earth rotates on its axis like this, we only end up in the sun for a very short period of time, and we spend more time away from the sun, which means the days are very short. Okay? The other problem with this is not only are the days short, but because we're tilted away from the sun, the intensity of the sunlight we receive is much lower. Okay? So we're getting less sunlight, and we're getting less intense sunlight, which contributes to winter. In the summertime, the Earth is still tilted 23.5 degrees, but now we're over here. Now the North Pole points towards the sun, which is why in the summertime, if you live in the Arctic Circle and your mom tells you come home at sunset, you come home in August. Because it's going to be daylight 24 hours a day for a while, right? As the Earth rotates on its axis, the North Pole never gets into the darkness. Okay? And because we're pointed more directly at the sun, we not only receive more hours of sunshine, we receive more intense sunshine. Okay? All right, this has nothing to do with Kepler. That's just why the seasons change. Okay, so quick review. That's why the season changes, not because the Earth gets closer to the sun. Okay? But the Earth does get closer and further away from the sun throughout its orbit. Now, according to what we know about the laws of circular motion, that also means then that the speed of the Earth has to do what? It has to change. Okay? I mean, when it all comes down to it, and Kepler didn't know this, is that the force of gravity is acting as a centripetal force. Okay? The force of gravity between the sun and the Earth is keeping it in a circle. Okay? And because centripetal force is related to these things, mass of the Earth is not changing, okay? But the speed of the Earth is changing because the radius of the Earth's orbit is changing. Okay? Sometimes we're closer, and when we're closer, we move slower. Okay, that's what we did for the radius lab, right? Okay, and when we get a little bit further away, we're moving a little bit faster. Okay, so we've got these points in our orbit where we move faster and slower. Okay, that actually means then that our seasons aren't the same length. Okay, we never think about this, but think about this. Why aren't all the months the same number of days? You ever notice that? I always thought that was the dumbest thing. Why do we have a month that's 28 days, and then we have a bunch of months that are 31, a bunch of months that are 30, and this month that's 28? That doesn't make any sense. Why wouldn't we just even it out? The answer is we can't. Because if we do, the equinoxes and the solstices won't end up on the right days. Winter and fall are our short seasons. Spring and summer are our longer seasons. Okay? When you think about it, in winter, you've got December, January. So December's got 31 days. January's got 30. Okay? February's got 28. Winter ends in March. Okay? That's the shortest season. Okay? September, okay, is where fall is, right? It's got 30 days. October's got 31. November's got 30. Okay? You look at your summer, okay? Look at your summer months, right? 30, 31, 31. Okay? 30, 30, 30, 31, 31. Summer's the longest season. Okay? And that's because that's when we're moving slowly. Okay? Everybody with me there? It's weird but true. Okay? All right, so Kepler's laws. Okay, Bray had made these meticulous observations about the orbits of Mars. Okay, we talked about that. Okay, and that's what Kepler used. So Kepler's first law is the law of elliptical orbits. Okay, an ellipse is an elongated circle. Okay, because there's elliptical orbits, then we have places where the Earth is going to be closer to the sun, places where the Earth is going to be further from the sun. Okay, and we're going to be moving at different velocities. Okay, now people are like, okay, that's wonderful. Prove it. So Kepler's like, okay, I'm going to develop this second law, the law of equal areas. And it talks about what happens in various time intervals. Okay, so if I have a bunch of equal time intervals during my orbit, okay, when I'm closer to the sun, I'm going to go through more of my orbit than when I'm further from the sun. Okay, but the area of each one of those sectors is the same. Okay, they just have different shapes. This one has a short radius, but a long arc. This one has a long radius, but a short arc. But the area of area 2 and area 1 are equal. Okay? That's how we prove that these things have elliptical orbits. Okay? So Kepler went on and he stated those. So if we're looking at the orbits of planets that orbit the sun, okay, these are their eccentricities, so how elliptical the orbit is. Right? So Mercury is 0.205. That means it's 20% away from being a perfect circle, so squished. Okay, there's a point in its orbit where it's essentially 20% closer okay, than its furthest point. Right? For Venus, Venus is almost a perfect circle. Okay? This is less than 1%. Okay? So it's almost a perfect circle. Earth, 1.7%. That's not much. Earth's orbit is pretty circular, but it's enough to make a difference of a couple of days on each season. Okay? For Mars, 0.93. Okay, so Mars's orbit is a bit more elliptical than ours is. Okay, Ceres, which is an asteroid in the asteroid belt, okay, about 8%. Jupiter, about 5%. Saturn, just over 5%. Uranus, about 5%. That's, by the way, how you pronounce it. Okay, Neptune, all right, about 1%, close to that. Pluto, look at that, 25%. Okay, and not only is Pluto's orbit really elliptical, it's also slanted. Okay? All the other planets orbit like this within that plane. Pluto orbits like this. Okay? Its orbit is so elliptical that there are times in its orbit where it's closer to the sun than Neptune. It actually crosses Neptune's orbit and is closer to the sun than Neptune for parts of its orbit. Okay? That's how elliptical it is. All right, and then these are Kuiper belt objects here, okay, and they have highly elliptical. Sedna is like a long period comet, right? It's really squished, okay, it's a super ellipse, right? So really, really long and really, really shallow. All right, okay, so you can see here, okay, what we're talking about, here's the difference in speeds. So when we're close, 109,289 kilometers per hour. Okay, when we're further away and there's less force acting on us, okay, then we go slower. Okay, sorry, I said that backwards, didn't I? Yeah, I did. Okay, so think about this. Okay, if I get, sorry, because it's dependent on not just radius. Okay, as we get further away, this number gets smaller. Okay, because as we get further away, R gets bigger. That makes FC get smaller. If FC gets smaller, V gets smaller. Okay? We did that in our lab, right? When we had smaller mass hanging. I don't know why I said that. Brain fart this morning. Okay, V will get smaller. So when we're farther away, we don't go as fast. So we don't travel through as much of the arc, okay, as we do here when we're going really fast. Okay, so we're closer, we're moving faster, we go through more of the arc here than we do over here. So this would be, okay, like our winter and summer. Okay, we're closer to the sun in the winter, so we get through more of our orbit, okay, faster. Okay, and then over here in summer, we stay there longer because we're going a little bit slower. And it's a significant difference. Okay, it's 4,000 kilometers an hour difference between perigee, that's here, and apogee over here. All right. Now, the only law that we have to really worry about of Kepler's law, so you have to know all three, because if I give you a multiple choice question, you have to know his law. So there's the law of elliptical orbits, law of equal areas, and then there's the law of periods. That's this law here, his third one. Okay. So if I give you a multiple choice question, it would be something like, which of the following is something Kepler would not agree with, or something along those lines. Okay. His law of periods was the kind of final proof that everything in the solar system orbits the sun. I don't think I have that in there. I'm going to have you write it down in just a minute because I've got it highlighted on the next slide. Okay, so his law of periods was the final confirmation that everything in the solar system orbits the sun, and it was the final thing that Tycho Brahe's data proved. Okay, what Kepler discovered, being a mathematician, was if you take the period of any body in our solar system, anything that orbits the sun, and square it, and then divide it by the cube of that object's radius from the sun, you get the same number for any object orbiting the sun. So if I take the period of Earth's orbit, square it, and divide it by the cube of Earth's orbital radius, I'll get the Kepler constant for our sun. I do that with Jupiter, I get the same number. Saturn, same number. Okay? All the planets in our solar system, all the comets in our solar system, anything that orbits our sun will have the same Kepler constant. Okay? Similarly, Jupiter's got like 50-some moons, right? And all of them have the same Kepler constant because they all orbit Jupiter. Okay, so this was where Tycho Brahe's data finally really did prove. The only reason why all these things should have this number in common is because they all orbit the sun. Okay? So what we can do with that is we can use information about a planet we know to find out information about a planet we don't. All right? So one of the things people knew was how long it took the bodies they were watching to make a complete cycle in the sky. So they'd be able to know the orbital period of the objects they could see, which would be Mercury, Venus, Mars, Jupiter, Saturn. Okay? They could see all of those moving in the sky. Well, knowing the Earth's information, they could figure out how far away those objects were, okay, using Kepler's law of periods. Okay. All right. These are Kepler's 3 laws. Write them down. Put them or add them to your notes package on your phone or whatever's going to be more convenient for you. Okay, I'll give you a couple minutes to write those down. We're looking for the orbital period of Mars if we know its orbital radius. Now, what other planet in our solar system do we know the orbital radius and orbital period of? Earth. What's Earth's orbital period? 1 year. Okay? Everybody okay with that? 1 year. All right. And what's Earth's orbital radius? 1 astronomical unit. Okay? The distance from the center of the Earth to the center of the Sun is the Earth's orbital radius, and it's 1 astronomical unit. So according to Kepler, if I take the period of Earth squared over the radius of Earth's orbit cubed, that will equal the period of Mars's orbit squared over the radius of Mars's orbit cubed. Okay, so I can solve for the radius of Mars's orbit by simply flipping these numbers, okay, and getting radius of Mars, okay, by itself over here. Sorry, we're looking for its orbital period. All right, so I'm going to bring radius of Mars over here, cubed, okay, and then I'm going to square root it all. That'll get me the period of Mars's orbit, okay, and it's going to be super easy to calculate because it's going to be 1.52 cubed multiplied by 1 squared over 1 cubed. Because remember, Earth's numbers are 1 year and 1 astronomical unit. What's 1 squared? What's 1 cubed? So if you can do the square root of 1.52 cubed, you will have the orbital radius of Mars, okay, in astronomical units. Okay. Or sorry, the orbital period of Mars, in years. Orbital period of Mars. All right. Tomorrow, you're going to be working on your circular motion assignment. I will give you all of class to do that after I introduce it to you and give you some tips and hints. Right? But that will be the plan for tomorrow. I will have it in Google Classroom for the start of tomorrow's class. Okay? So I will also be putting up the date of the unit exam because we're now halfway through the unit. Right? So I'll be putting that up pretty quickly here so you know when it will be.